Okay, folks, let's take a look at number 3. Question number 3 is one of the more challenging questions in a calculus class, and it requires us to use the fundamental theorem of calculus part 1. So I'm going to put that off to the side because you've probably forgotten it. The fundamental theorem of calculus part 1 says that if we were to take g of x as our area function, so let's first start with an underlying function, let f of x be a function, and we'll just go ahead and add continuous function. We don't really need that. We could relax that slightly, but we'll just go ahead and say continuous function. Okay. On a to b, and then for x, we'll consider x values within the interval from a to b. So if we have the function g of x is equal to the integral from, let me just put c to x of f of t dt, okay, for some fixed c. This is important. It needs to be fixed. Some fixed c in AB and some x in AB. Then the fundamental theorem of calculus says that g prime of x is just f of x. And that should be what we saw in our solutions when we explored number 1 and 2. So number 1 and 2 are really meant to give you a intuition as to why the fundamental theorem of calculus part 2 is true. Or excuse me, part 1 is true. So let's go ahead and continue this while I close the window. Okay, so all of these problems here require us to in some way apply this fundamental theorem of calculus part 1. The first two are very straightforward. Okay, so let's go ahead and do letter A. This asks a question. Here's g of x, and it's our area function, and it says, what is the derivative of this? Well, g prime of x, the derivative of the area function, as we saw on these previous pages, is simply the underlying function, e to the x squared. Folks, I did no work. No work required on this problem. All I simply did was say, hey, what dictates how my area function changes? And the answer is the shape of the function that we're taking the area beneath. Okay. So now g of x, or letter B here, is another one where we can simply go ahead and answer the question with no work. G prime of x is simply 3x squared minus 3. That's by the fundamental theorem of calculus, part 1. And let me just add, no work needed. Okay. Now, what's another way to do this? Well, in this case, and this is actually the only, of all the problems on this page about the fundamental theorem of calculus part 1, this is actually the only one where I could compute this what I call the long way. Okay. So I don't want you to do this. Don't do this. But let me show you another way to arrive at this answer. Instead of using the fundamental theorem of calculus part 1, let's go ahead and use the fundamental theorem of calculus part 2. So I'm going to go ahead and evaluate this because in this case, unlike all the other functions I've got here, I can actually compute an antiderivative to this function. An antiderivative of this function would be t cubed minus 3t evaluated from 0 to x, which gives me x cubed minus 3x minus a whopping 0, or just x cubed minus 3x. Now I'm going to go ahead and take well, let me just say that means that another way of writing g of x is that g of x is equal to x cubed minus 3x. So now I can go ahead and take the derivative of g of x just as I normally do. This is not using any current material. This is how we used to compute derivatives. We get 3x squared minus 3. And notice we end up with the same answer as before. This really helps to see that the antiderivative, the definite integral, is in a way an inverse operation of the derivative. That gives us some insight into that relationship anyway. I don't want you to do most problems this way though. Instead, we were able to answer that immediately by saying, what is the derivative of the area function? It's simply the underlying function now evaluated at x. And there was no work needed. In this case, and in this case only, we were able to justify that answer a second way, looking at the fundamental theorem of calculus part 2. Now these problems get a little bit harder in that going forward I will have to do, for the rest of these, I'm going to have to do some sort of chain rule in these problems. So for example, if this were the function h of x equals the integral from 5 to x of the square root of t squared plus 4 dt, then I could just say that h prime of x is the square root of x squared plus 4. And one way to look at what I just did, although this isn't really what we're trying to learn, is that I simply replaced the t in the expression here with an x when I gave the derivative. Well, in this case, look up here, what have I got? I've got something more complicated than just an x. So I can go ahead and mimic this procedure, but I'm going to have to do the chain rule. So here we go. We would find that in this case, for our problem, g prime of x is equal to the square root of, and then in place of t squared, I'm going to put this upper limit of integration. So I'm going to put in place of t squared, I'm going to put x squared plus x, quantity squared, plus 4. But here's the rub. Because this expression up here was more complicated than just an x, I need to, by the chain rule, multiply by the derivative of that expression. And so bringing that derivative out front, we get 2x plus 1 times the square root of x squared plus x squared plus 4. Okay. So this really was, again, just an application of the fundamental theorem of calculus. The difference is that I replaced the t with the upper limit of integration, but I had to perform a chain rule on this. So let's go ahead and look at letter D now. This is very similar. I'm going to let you do D on your own. Okay, you try. Okay. Use letter C here as your guide as you work through letter D. Okay. It's the same problem. It's just the function upstairs has changed from an x squared plus x to a sine of x. Okay. Okay. Now we're going to look at letter E here and letter F. Both of these are going to require a little bit of adjustment using our properties of integrals prior to applying the fundamental theorem of calculus. For the first one, notice I'm still just rewriting g. I haven't gotten to find its derivative yet. I'm going to use a property that says if we want to interchange the limits of integration, we can do so, but that changes the sign on our, what was in the Riemann sum, either the delta t or the delta x. If that changes sign for all of those, I can go ahead and factor that negative out. So if I interchange the limits of integration, I can do so, but I have to put a negative sign in front of the integral. So this is a better formulation of the problem. How come? Because now this looks like my fundamental theorem of calculus, which would tell me what to do if I had a to x of the square root of t squared plus 4. So now that looks like this, except that this expression here is more complicated than just an x. So when I go to apply, however I take this derivative, I'm going to do the same thing here, but I've got to do a chain rule. Okay, let me go ahead and clear that out. All right, so when we go to find g prime of x, this minus sign just follows along. The fundamental theorem of calculus says we get to replace the expression in the integral symbol when I'm dealing with this area function, and only when I'm dealing with this area function, I can replace the variable t squared with e to the x squared plus 4, but then I'm going to have to multiply that by the derivative of e to the x, or whatever other function is up there. Cleaning this up, we get that g prime of x is equal to negative e to the x times the square root of e to the, e to the x squared is just the same as e to the 2x, because we're multiplying e to the x to e to the x, plus 4. And there is the antiderivative of this particular area function. Okay, I'm going to let you try letter F on your own, but let me get you started. And the first thing I'm going to do is I'm going to break this problem up into two separate pieces. I'm going to go ahead and say that this is the integral from x to the 4th all the way up to, I don't care which value I pick, let's pick the value 0, square root of t squared plus 4 dt, plus the integral from 0 to x of the square root of t squared plus 4 dt. Okay. So what I did was I broke this integral up at some fixed number. Okay. Why did I need some fixed number? Because if I want to apply the fundamental theorem of calculus, I need c, that lower limit of integration, I need that c value to be a fixed number. So now I've introduced, now each integral has its own fixed number in it. Now this piece right here is ready to apply the fundamental theorem of calculus to. It's all set, ready to go. But this piece right here, again, needs some adjustment. How come? Because the fundamental theorem of calculus, this theorem only applies if the lower limit is c and the upper limit is x, or some expression involving x. So we can go ahead and rewrite this one more time and say that g of x is equal to the integral from 0 to x to the fourth times the square root of t squared plus 4 dt plus the integral from 0 to x of the square root of t squared plus 4 dt. And now you have too many fundamental theorem of calculus problems to do when you go to find g prime of x. So I'll let you finish that out. Let me just say that this first one here, will require a chain rule, whereas this one will not. And if you're having any questions or concerns about that, look at what we did in C, look at what we did in E, and look at what you did in D. And putting all those pieces together, you should be able to see how to do this problem. Okay, I'm going to let you guys do this review of indefinite integrals on your own. There's no new material in here, and you've practiced this all before. Notice in this one, I don't think that you have the tools to find an antiderivative of tangent cubed of x. That's something that you'll learn how to do in Calc 2, but if you're just taking Calc 1 for the first time, I don't expect that you would know how to take an antiderivative of tangent cubed. It turns out, I claim, at least, that this is an antiderivative of tangent cubed. I would like you to verify through differentiation that this is correct. So I want you to take d dx of 1/2 secant squared of x plus the natural log of the absolute value of cosine of x plus c. I want you to take the derivative of this expression, and you're going to do some work, and don't write this part. You're going to show some work, and eventually you're going to show that that's equal to the tangent cubed of x. Okay? Note that you're going to have to at some point use the identity that the secant squared of x minus 1 is equal to the tangent squared of x. So at some point you're going to need to use this Pythagorean identity on this problem. Okay. Other than that, I'll let you try these on your own. I think this is a fair game problem. This is a fair game problem. So just go ahead and pause the video and work those these three problems.